was full when a car or something
GPS tracks us to keep position.
Orbits have always been at the intersection of astronomy and physics. Ever since the earliest days, people looked up at the night sky and they could see with their eyes that stars rose and set. And they could mark out that there were things different from the stars, which we now call the planets. And so they wondered how things moved in the sky. The very earliest historical records show already sophisticated knowledge of these motions. And so presumably people were already keeping track of these by oral traditions thousands of years before what we would now call civilization. However, it was only in the last 400 years that our modern conception of how planets actually orbit the sun work. It was in the mid-1500s that Copernicus started his revolution by saying, geez, maybe the planets revolve around the sun. And Kepler then set down his laws of planetary motion in the early 1600s, which was just a description of how that motion worked. And it wasn't until the latter half of the 1600s that Newton came along, and with the apocryphal apple falling on his head, realized that the falling of the apple was the same as the trajectory of some projectile thrown across the room, or the moon falling in its orbit, or the planets moving in its orbit around the sun. These were all the result of the same effect, what we're here today to talk about, gravity. And all of these things could be quantitatively explained and predicted with his universal law of gravity. And it's a very interesting thing. When he stated this, he said, everything happens as if the force between two objects is the product of the masses and inversely proportional to the square of the difference. And I emphasize the as if because at the time it seemed like magical thinking to imagine that the sun could reach out and push the planets around. How could you have action at a distance? It wasn't understood then. But the formula worked. Everything worked as if that were what's going on. Well, almost everything. So at the time, Newton sort of despaired of ever being able to calculate this in any great detail because he realized that not only did the sun exert a force on each planet, but each planet exerted a force on every other planet, and it very quickly became a complicated exercise that he actually wrote that I don't think humanity can do this. Within 200 years, mathematicians had developed techniques to do exactly that, and this was long before the modern computer. At the same time, astronomers continued to keep close tabs on the positions of planets, and they noticed a slight discrepancy in the orbit of the planet Mercury. Right, so Mercury has an elliptical orbit, which is greatly exaggerated in this figure, and the orientation of that orbit slowly precesses around. So it changes over time, again, greatly exaggerated here. The amplitude of this motion is about 573 arcseconds per century. An arcsecond is 1/60th of an arc minute, which is 1/60th of a degree. It's a tiny angle. But by the middle of the 1800s, this was already well measured. And so well measured that we could also calculate what the effect of Jupiter on Mercury was, Earth on Mercury, all the other planets, and confidently say that that was 43 arcseconds per century too much. It wasn't quite right. Newton explained everything except this tiny discrepancy. This was not solved at the time. People thought the most natural explanation was that there was another planet that hadn't been discovered, and they deemed this planet Vulcan, worked out that it had to be between the sun and Mercury, and went looking for it. Many people claimed to see it. Nobody could confirm that. Nobody ever found Vulcan. So this sort of, over the decades, passed into a mystery that was just better left unsolved. Until along came Einstein and worked out the general relativity theory that we've been talking about today. And one of the early things that he worked out as a consequence of this theory is, of course, that you recover Newton and everything that he had taught us as one limit of his theory. But when you were close to the sun, like Mercury, it was a little stronger in effect. And he worked out that you would get exactly this extra 43 arcseconds per century as a consequence of his theory of general relativity. So it naturally explained this long-standing problem and is one of the things that propelled general relativity to being widely accepted. Now we flash forward to today, and we have another problem: the orbits of stars and gas and galaxies. Galaxies are naughty. They do not follow the law of gravity as taught to us by Einstein and Newton. And in this regime where a galaxy's orbit is a very weak field regime, you don't need to worry about the very strong field things that happen with black holes that we've been talking about. Newton and Einstein predict the same thing. But you can observe these things rotating around. Just by looking at the picture, you get a sense of how the rotation happens. We can measure that quite accurately. And that rotation does not do what we expect. So this is a rotation curve of that very galaxy. It measures the speed at which things are traveling around the center of the galaxy as a function of the distance from the center of that galaxy. And that line there is what you calculate for the law of gravity as we know it, given the distribution of stars and gas that we can see. So this is what you expect to get. This is what works extremely well in the solar system and every other system up until you get to galaxies, and then in galaxies you get something like that. The rotation speed is faster than it should be. And this discrepancy, like with Vulcan, we usually attribute to dark matter. There's some extra mass there that's making things go faster. And this is the norm. So in the late 70s, early 80s, Vera Rubin using optical telescopes, and independently Albert Bosma using radio telescopes observed many, many spiral galaxies and found over and over and over again that the rotation curves came approximately flat as you went further out. They rotated too fast for the stuff that you could see. This was essentially a law of nature that they discovered. It always comes out that way. Now, my colleagues and I have worked to extend this kind of observation to lower surface brightness galaxies, things that are harder to see. These galaxies are often lower luminosity. They have fewer stars than the ones studied earlier. And the stars are more spread out. That's what I mean by low surface brightness. So if you look at the pictures of galaxies there, the ones that are easy to see had been the ones that had been studied early on. Those were high surface brightness, where the stars are crowded together. But if you spread the stars further apart, you see the lower version. It's not much to look at, so I can turn up the contrast. And you see there's the same kind of structure, the same kind of spiral arms, and we can measure the same kinds of rotation. And that's what you see for these lower luminosity galaxies, that they still have flat rotation curves if you get far enough out. Another thing that was discovered empirically was the so-called Tully-Fisher relation, discovered by Brent Tully and Rick Fissure there. And they realized that galaxies rotated faster if they were bigger. So in this diagram, each point is one galaxy. That rotation speed, VF, that's the flat level of rotation velocity. The other axis is the mass of the stars in the galaxy. The more stars, the faster it rotated. This was essentially another law of nature that I got interested in understanding physically why it worked. And so as I started exploring lower mass galaxies, I found that they started to fall off of this relation. But I didn't realize that these galaxies were mostly made of gas, not just stars, as was originally in the empirical Tully-Fisher relation. So the more fundamental relation here, another law of nature as best I can tell, is that the rotation speed correlates with the total mass. And it doesn't matter whether that mass is in stars or in gas. It's the sum that matters. And when you include both of those, you recover this very strong correlation over almost 6 decades in mass. Now, to an astronomer who works on galaxies, this is like magic. Whenever you plot the properties of galaxies against, you can measure the size, the speed, the color, all sorts of things, it's usually a mess. You got galaxies all over the place. And so when you see something like this that has very little scatter, and in fact you can quantitatively account for how much scatter is due to the observed errors, and the relation is consistent with 0 scatter. There's a very tight relation. And it doesn't matter If it's high or low surface brightness, that's what the color codes there. The high surface brightness galaxies are doing the same things as the low surface brightness galaxies, and that confused me mightily. Because Newton taught us that the rotation speed depends on both the mass and the radius, how much these things are spread out. Here I was specifically looking at things that had different radius at a given mass, different surface brightness, and yet they were rotating at exactly the same speed. The data were disrespecting what Newton taught them. And this is an illustration of how bad that is. I've now only color-coded the points by whether there's more gas or more stars in the galaxies. And you can see there's no residual from this Tully-Fisher relation. It's just the data are flat. That dotted red line is what Newton predicts it should be. So this struck me as an anomaly, something that simply should not happen. You take an important component of the mass, the stars and the gas that you can see, you spread it around by different amounts, and the galaxies don't care. Now, I was pounding my head against this problem when I happened to encounter this chap here, Moti Milgram, who's an Israeli physicist, and motivated by flat rotation curves, he had said, well, geez, maybe it's not dark matter. Maybe we need to tweak the force law to change the law of gravity just a little bit. And he suggested doing this at a particular acceleration scale. Now, the first thing we think about of galaxies is they're much bigger than the solar system, where general relativity and Newton are extremely well tested. Okay? But that's not the critical thing about galaxies that matters. It's not the size, it's the acceleration. And the centripetal acceleration that holds stars in their orbits around the galaxies is tiny by human standards, about 1 angstrom per second per second. Well, it's sort of an atomic scale thing. That's 1 part in 10 to the 11 of what we feel sitting in this room. Tiny, tiny acceleration where things seem to change. And so I was impressed that he had said a few things that explained what I was seeing, and so I thought I should look into it more, and I actually read his original paper. And I was amazed to see this sentence that disk galaxies with low surface brightness provide especially strong tests. That's what I was doing. I was looking at those kinds of galaxies because I was interested in how they work. Not because I wanted to test this theory. I had, by accident, done the right experiment to test this theory that he'd come up with. And the thing that amazed me right away is that even though this had been proposed long before I collected any of these data, it explained the Tully-Fisher relation really well. It had the slope, the normalization right. Fundamentally, it was telling you it's just a relation between that flat rotation velocity and how much mass there was in stars and gas. But the thing that really attracted my attention is that he explicitly said there would be no dependence on surface brightness. Unlike the Newtonian limit, he's now talking about a new limit that hadn't been explored by Newton or Einstein. It's very low acceleration dynamics. And in that limit, only the mass matters, not the radius, which is exactly what I was seeing and not understanding in the conventional context. So what I had predicted based on Newton was wrong. What he had predicted was right. He made other predictions, one of which was that if you looked at the discrepancy relative to Newton, what Newton predicts for just the stars and gas that you see is that solid black line at 1. He said, well, in those high surface brightness galaxies, you won't see much of a discrepancy because the accelerations are still high there. But as you get to these lower accelerations where this new limit he proposed kicks in, then you should start to see the discrepancy appear. And that's what you see in those lower rotation curves. But as you go to lower surface brightness galaxies, already you should have a large discrepancy at large radii. And again, that's what we saw. He also predicted what the shapes of rotation curves would be, that the high surface brightness things would go up very fast and then flatten out. But as you went to lower and lower surface brightness, you would have a more gradual rise of the rotation curve and only gradually flatten out. And again, that's the segregation you see in the colors here going from high to low surface brightness. Fundamentally, what he was saying is that the gravity was being sourced by the stars and gas that you could see. And so the higher the surface brightness, the stronger the force. Therefore, the higher the acceleration. So this is a plot of each of the rotation curves as the acceleration that's needed to keep these things stable as a function of radius, color-coded by surface brightness again. High surface brightness means high acceleration, relatively speaking, for a galaxy. Low surface brightness means low acceleration. And again, you can see the segregation by color, which is exactly what he was predicting. This was a new force law, right? This was not any mild hypothesis. He's suggesting that there's more to the story than just Newton and Einstein, that there is a new regime where the force law is different. And so if you feed this mathematical formula that he came up with, the distribution of mass, then it should be able to predict the rotation curve. And basically what this amounts to is a formula for going from Newton, that black line, up to what you actually see, the blue line. And that has to work in detail for each and every galaxy independently. So it works not only for the high surface brightness galaxies where the discrepancies are small, but for the low surface brightness galaxies where the stars are spread very thin, the accelerations are very low, and the correction he predicts is large. And yet it works very well, including preserving some strange features that you wouldn't otherwise expect to be there. And you can do this as many times for as many galaxies as you have the patience to do. You can do it over and over and over and over again. So I've cobbled all that together in this one residual diagram. This is the difference between the data and the Mond fits to each galaxy for 78 galaxies, over 2,000 individual points in the galaxies. The agreement is good. So you could make these detailed fits to the rotation curves of all these galaxies. That means the force law is working, at least in these systems, of which we've now examined over 100, not all of which I got on this plot. Now, when you make these fits, there is one fit parameter, one unknown that you can play with. What you need to know for the theory is the mass in the stars. What you observe is the amount of light from the stars. So you have a mass to light ratio that you can adjust. And each of those fits had that adjusted to the optimal value. Now, at this juncture, we as astronomers think we know quite a lot about stars, and so we have a clear expectation value for what those mass to light ratios should be. So that provides another test. Here's a plot of the mass to light ratio on top in the optical part of the spectrum, on bottom in the infrared part of the spectrum, as a function of the color of the galaxies, or bluer galaxies on the left, redder galaxies on the right. And we expect what that blue line shows, that the optical mass to light ratio should get higher as you go to redder galaxies because those are made of older stars. But that shouldn't matter as much in the infrared, so you get a flatter relation. That line is from population models that have nothing at all to do with Milgram's theory. Completely independent information. What's more, those population models also tell you about the scatter. And you expect more in the optical than you do in the infrared. So that one free parameter that he has in making these fits has an independent astrophysical test, and it agrees as well as you could possibly hope for it to agree. Okay. It's completely unexpected. I didn't think it could possibly be true, but I was dragged into this by the data. So at this juncture, I would say, echoing Newton, that everything happens in galaxies as if Mond were the effective force law. Okay. I don't know why. I say as if, because I do not have a good physical understanding of why this happens. It should not happen according to Newton and Einstein. So it says there is something more still to the story than what they told us. Now, I've continued to try to test this theory. It would take all day to talk about all those things, but a relatively recent test comes from the dwarf satellite galaxies of our nearby giant companion spiral, the Andromeda Nebula. So what you see here is a black blob is the Andromeda Galaxies. Has been surveyed very thoroughly to find some of these really low surface brightness dwarf satellites, an example of which is circled in blue. These are just little tiny puffballs of galaxies that are very much in this low acceleration regime. And what I realized is that as people were doing the survey, they were telling me how many stars were there, and I could use that information to predict, a priori, how fast those stars were moving. And in effect, they fell along this Tully-Fisher relation extrapolated to still smaller masses. And now we're getting down to things that are only 10,000, 100,000 solar masses. That's a star cluster. That's nothing by galactic standards. It's a very tiny system. Now, this is what you would do empirically if you didn't know about MOND. But MOND has a very peculiar prediction that it depends for these things. If they're close in to their host galaxy, they can be affected by the gravity of that host galaxy. And if they're far away, they're not. And it gives you a criterion. And so that's why there are two different colors there. The red things are far enough away, they shouldn't care much about what their host galaxy is doing. The green things should be affected by that external field in a way that is not natural at all to Einstein's gravity. Einstein would say that the external field never matters, it's all local. But you apply this MOND correction, and it looks like that. Lots of scatter, very little scatter. So these galaxies know about this formula that Milgram wrote down. Makes no sense at all in terms of what we thought. And yet, there is some empirical validity to what's going on. So I take this away as a good thing. Science is not over. There are still very fundamental things left to learn, because we do not understand how to explain this in the context of a relativistic theory. That is an open theoretical problem. One of the leaders in doing that was Jacob Bekenstein. He worked on it for many years, had many failures along the way. In 2004, finally thought he'd gotten something that merged Milgram's hypothesis with Einstein's in a theory he called TEVIS. I don't think that's the final word on things, but it was an important demonstration that this seemingly impossible theoretical task might actually be possible. And I wanted to mention him especially because, unfortunately, he died just a few months ago. So he was one of the leading lights of relativity and gravity theory. But I think he would be happy to know that this can still go on, that there is still something to learn, and that science is not over. There are still fundamental things left to be discovered. Thank you.